let's continue our lecture. So next we talk about how to evaluate our class 3 performance. Okay, so this is the first one. Okay, so we can measure their purity or accuracy. Okay, so here we have the Y is the class label set, and the C is your cluster label set. So in your experiment, you want to evaluate the result. Okay, so here we usually assume that each data point we have a class label. So remember, in training stage, we cannot use the class label, okay, because it's unsupervised. But in evaluation, because you want to evaluate the accuracy, so you have to use this class label. Okay. Okay, so you have the class label for each data point, and also you generate, based on your class 3 algorithm, you generate a class label set. And here is an example, and we have generate 3 clusters, and each clusters you can see we use a different data. The data point we use a different symbol to represent its class label. Okay, here you can see we have close, the circle, and the diamond. We have 3 different classes. And now, after our classroom, okay, we generate the 3 clusters, and these data points are assigned to the cluster correspondent. Okay, so it's our result. So we want to evaluate what is the performance, its accuracy. Okay, so first is we call it the purity, or call it accuracy. So it means for each cluster, we find a major class so that we can measure its accuracy. So the idea, the expression is like this. The purity is given the Y and your label, class label set, and the cluster label set. Okay, you can calculate the accuracy like this. It's actually your label, your class label intersects with your class label, and we want to find the maximum K. And it means I want to find which K cluster is maximized here. Here is we use the example to illustrate the idea. Okay, so we have 3 clusters. And for each cluster, we first find this major class. Major class here for cluster 1 is close, right? Because close has a more number of the data points in cluster 1. So the major class will be close. There are 5 in cluster 1. And in cluster 2, the major class will be circle, right? And there are 4 circle points in class 2. And in class 3, we have the major class diamond. It contains 3. And so the purity is computed like this. Okay, we have to count each for each class. Okay, we just count. Okay, we count. Okay, here in cluster 1 we have 5, and class 2 we have 4, and class 3 we have 3. We just count how many data points belong to the major class, and time with just average it, the total number of your data points. So here the purity can be calculated like this. So it's a very easy way to calculate the purity of each class. Okay, any problems? Okay, so it's an ideal case. So you can easy to find each. Okay, in here each class can be assigned to just one cluster. But sometimes your clustering algorithm cannot perform as well as this. So maybe you will find some class that belong for the class 1 and class 2, they have the same major class. Sometimes you will find this situation. Okay, so you have to assign the best match between the cluster and the major class. Okay, so there's in such a situation, there is to find the best matching between the class and the clusters. You can use the Hungarian algorithm. This algorithm can help you to find the best match for each cluster. So we can assign this one should be which class, and this one should be another class, so they can make their purity to be maximum. Okay, so you can combine the Hungarian algorithm to do the computation. Okay, so any problems? So it's called the first metric called purity. And the second metric is called normalized mutual information. Okay, here are two different expressions, but they are similar. NI can be for the Y class and for the C clusters. You can compute like this. I think the main idea is how to calculate the mutual information between Y and C in the numerator. Okay, for the denominator, it's just to normalize it. Okay, so you can ignore the numerator here. The main part is the mutual information between Y and the C, between your class label set and the class label set. To compute the mutual information, actually here they apply the entropy in information field. So we have to compute the entropy to reflect the mutual information. So here comes the example, and we will show how we calculate. Okay, suppose we have three classes, and in this algorithm, in our clustering, we just only two clusters. Okay, so we have two clusters, but actually they are three different classes. Okay, this first clusters, and you have these different labels as the class labels. You have a triangle, square, and star, three different classes. Okay, so it's the second cluster. Okay, we have three classes. And then we have to compute the mutual information. Okay, we use the entropy. So do you know the decision tree? So in decision tree, there is you have to use some metrics and some measures to determine which attribute to be used to divide your set into several subtrees, right? So one of the metric to determine which attribute is the best is use the entropy. It's called information gain. So do you know this? The decision tree. Okay. Okay, so this is similar to decision tree, the general idea. Okay, so let me show how to calculate. Okay, first we can calculate the class label entropy. Okay, so here it means because you just consider your total data point, consider all together. Okay, and there are 20 data points, and there are three different classes, right? So for class 1, Y is 1. For class 1, there are 20 data, and 5 of them are class 1. So you can calculate their probability like this, right? And for class 2, there are 10 of the data points belong to class 2. So there are 10. Class 2 is the square, right? The blue one. There are 10 in total. Okay, so here the probability is 0.5. And for class 3 is 0.25. Alright, so it's represent the probability distribution of the three different classes. Alright, so we can calculate the entropy. So recall the entropy equation. It's is like this. Entropy. To calculate entropy. So, given you a probability distribution state, like P1, P2, until Pn. So it means you have n different probability distribution. You can consider it as a state, a specific state. You want to calculate which entropy. Okay, the equation is like this: -1 P1. This can be expressed like this. It's called an entropy. You just calculate the probability. P1 to Pn are probabilities. They should be sum to be 1. And we call it a probability distribution among the different, here is classes. And that can be calculated like this: negative P1 times log P1 minus this. And the entropy is just to you can express you can interpret it as an uncertainty of this probability distribution, or you can interpret so if we want to encode this probability state, distribution state, how many bits, how many information contained in this probability distribution, and how many bits I should use to encode this probability state. Okay, so it's called entropy. So the unit we use here is bit. Okay, so if your entropy is like this, for example, your entropy is like this. Suppose you have a dice. It's a four-sided dice, 四面赛的. So the dice you will show is for the phase 1, the side 1, side 2, side 3, and side 4. They have the equal probability. Okay, so what's the entropy? Based on this equation, you find this entropy is like this. So the answer is 2 bits. So it means under this probability distribution state, the uncertainty is 2 bits. Or you can say you need 2 bits. This information is 2 bits. The average is the expected information is 2 bits to encode this probability distribution state. Okay, so it's the one way to calculate it. 好，这 entropy 之前有学过吗？有吗？有什么课程有学过？Okay, so you just think entropy, you try to encode the uncertainty of the distribution. So the entropy, if the entropy is high, means its uncertainty is high. you need more bits to encode this state. If the uncertainty is low, this means you don't need to use it. And you can use less information, use less bits to encode it. Let me show, suppose your entropy like this. So this is a four-sided dice. Okay, if they have an equal probability, you can use 2 bits to encode it. Okay, so means you need 0, 0 to encode the number 1, for number 2, 0, 1, for number 3, 1, 0, and the number 4 is 1, 1. You can use this, and you can find this entropy is the lowest information you can achieve. And how about if your entropy, if the dice is like this, 1, 0, 0, 0. It's always, the number is always 1. When you rotate the dice, always the number 1 show it. Okay, 就是这个市面上每次都只会转到1嘛。Okay, so what's the entropy? So you can calculate like this: 1, log 1, and the others are 0, so you can ignore. Just okay, and the bit is 0 bit, right? Yeah, because log 1 is 0. Okay, all the others are all 0. So it means you just use 0 bit to encode the probability state. This is because you always show the first state, right? Okay, you don't contain any information here. The uncertainty is 0. You just make sure each time you just show the number 1. So there is no uncertainty. So you don't need to use any bits to encode essential state, because you can 100% show that the dice always show number 1. Okay, so if the entropy is if the uncertainty is small, the information is low. If the uncertainty is high, like this, the entropy will be high. Okay, so we use this. We can use this idea to measure the impurity. Okay, if the cluster contain very pure, all contain the same cluster, all in the cluster, all the data they belong to the same class, it means the cluster is very pure. And when you compute the entropy will be 0. So we can also, so that's why we use this idea, the information theory, to measure the cluster performance. So if your cluster contain all the same class labels, then entropy will be just 0, very low. And the low entropy means your performance is good, because they are pure. Okay? Okay, so we just follow this. Okay, so now we have 3 probability, and 3 probabilities: 0.25, 0.5, 0.25. Just sum. The summation is 1, right? Okay, so compute. Based on this state, we compute the entropy. 1.5 bits. Okay. So the entropy means is the optimal expected value for the information to encode the probability state. Okay, so next we calculate the entropy for the cluster labels. We have two clusters. Each cluster contains 10 points, right? So this data belongs to cluster 1. Okay, it contains 10 points, so the probability is 0.5. If for the cluster 2, the probability, the data point belongs to cluster 2 is also 0.5. So the entropy can be calculated at least 1 bit. Okay, so next we define the mutual information like this. The mutual information is the entropy of Y subtract from the entropy of Y given C. Okay, so what's the Y given C? Entropy of Y given C means the entropy of the class labels with each cluster. So I give the clusters here. So what's the entropy is shown to be class Y. Okay, so here is how we calculate. Okay, first, if you know the decision tree, so the idea is actually the same to the decision tree. So you can recall the information gain method. So the idea is the same. Okay, so here I will not repeat to say it again. Okay, but here just give the example how to calculate it. So first we consider cluster 1. For cluster 1 here, given cluster 1 and the probability to be first class is 0.3, right? Because there are 10 points and the 3 of them are class 1. So the probability is 0.3. And for class 2, the probability is also 0.3 because the class 2 is the blue square, only 3 here. And for class 3, there are 4 star in cluster 1. So the probability is 0.4. So based on this, you can calculate the entropy for given the cluster 1. Okay, so here is the first we time is the probability of the cluster 1 here. Okay, you have 2 clusters. Okay, so you belong to the cluster 1 is 0.5 here. And for the next terms, they represent the entropy. Okay, so the entropy you see here. We calculate the entropy. This summation just calculate the entropy we mentioned earlier. So you can see calculate like this. You just take all the probability distributions, calculate their corresponding entropy here, and you get the result. Any comments? And consider the class 2. Okay, we just repeat the same process. Okay, you can find its entropy is 0.557. Okay, so the information, the mutual information based on this equation. Okay, just take the 2 entropies, subtract the original entropies. It means before you do the cluster, before you apply the clustering, all the data they just mix together, right? But after you apply the cluster, you divide the data into 2 clusters. So eventually, the data in the clusters are more pure. Okay. After your clustering, if your clustering is good, actually you can generate a pure classification result. Okay. So this means you should be lower. The entropy will be lower. So it's the original entropy before clustering. Consider all the data. But after your clustering, you divide into 2 clusters. It should be pure, and the entropy should be lower. Okay, so actually you will generate a positive result. This means how much information you will reduce after your clustering. So if you can reduce higher, you can reduce more, means your clustering is better. Okay. Any problems? Okay, so finally this one is a normalized term, but you can ignore this part. You don't need to do the normalization because we will consider 2 different methods, and there is the first method we show our normalized mutual information. It's like this, and there is a second a different clustering algorithm, and it performs like this. So we can compare. We want to compare which one is good. Then use the N and I. Define the second clustering algorithm can get a higher N and I. So it means the result is better than the first algorithm. Okay, do you agree? Just visual inspection about the 2 results. Which one you think is better? I think the second one, right? Because the second one is the class label distribution is pure. It's more pure than the first one. Do you agree? Okay, so that's why we get a better result, get a higher NMI by using the mutual information calculator. Okay, so it means the second algorithm, clustering algorithm, is better. Okay, any problems? Okay, so next is some other major, but I will skip it because I already mentioned in our introduction for information retrieval. So skip it here. Okay, so let's give us some discussion on the chemistry. Okay, so the algorithm is trying to minimize the square distance to the cluster centers between all the data points. But the result can be very significant based on your random seed. Remember the k-means, the first step is to randomize a k-centroid, right? So it's dependent on your random seed. So the result can be different significantly. So here is a very big example like this. So suppose we have 6 points is arranged like this, and if your random seed is start from the D2 and the D5. So what's wrong? What's the clusters? You want to generate 2 clusters, but your random seed is D5 and D2, and it's just located at D2 and D5. What happened? Sorry, I think I should just draw on the slide. Let me draw a picture just over here so that our recording can keep the trajectory. Where is our okay, so if you if I want to generate two clusters and the initial cluster centers is at D2 and D5, what happened? The result will be like this. You will separate the data into two upper and down. Top cluster and the bottom cluster. It looks strange, right? We should intuitively we should separate it into the left and the right. It should be like this. But if your random seed is just unfortunately like this, you will generate a very strange cluster result. Okay. So if our seed is D2 and D3, the result will be totally different. Let me so if the two seed is at D2 and D3, the clustering will be like this. Okay, so it looks better, right? According to their data distribution, looks better. It's what we want. Yeah, so it means sometimes if you are unlucky and you're lucky, it's not a few, it's just a few, you will generate a very different result. So how to solve it? So just restart with different application. Maybe you will restart 5 times and to check which one you get the minimal loss, and you can choose this one. Okay, so it's the first issues you have to know when you run the k-means. K-means you already have unlike you can already have a library. You just run it. It's just single line to specify how many clusters you want, and it's easy to run it. But you have to run several times to make sure you will not trap into such a local optimization. Okay, and how about the time complexity? The computation, okay, between any two vectors is suppose it's a big O of D. D is your number of dimensions, and when you do the reassignment in our Indian algorithm, to do the reassignment step, okay, you need to compute k is the number of centroids, and n is the number of your data points. So because each data have to compute which centroid is closest, so I have to calculate with all the centroid. Okay, you have kn ties with their dimensions. And to do the computation, just do the average all the data, and to calculate the new centroids. So the time complexity is ND. So just combine the two together. So the KND dominate. So the main computation cost is from the reassignment. And we will iterate I times. So suppose I is usually said to be 50. Okay, so you will repeat it 50 times. Okay, so it's the total time complexity for k-means. Alright, so actually it is very time consuming if you have a large data set to be trained in k-means. But k-means is already the most efficient. Other clustering method take much time. So that's why K-means is so popular. It's widely used because it's very efficient, and the performance is also you can consider it's still very good. So you don't need to spend so much time to use other complicated algorithm, but you just improve a little bit. So maybe it's impractical in most cases. So that's why K-means is still the most popular method if you want to do clustering. So but there are some way to speed it up. You can use phase library. The phase library already provide you just one line to do clustering, and it's take the advantage of use multiple CPU and GPUs, so you can accelerate it so much. And there's also some method use the PQ, quantum quantization. Use the quantization technique to do K-means. Okay, you can do it claim you can do a billion scale clustering. Okay, so but if you really encounter a billion scale training data, the simplest way is to do sampling. You don't need to use the 1 billion data to do training. You just sample it. Maybe just sample it to be only 1 million data point to do your training. You can save a lot of time. Yeah, but although the result is not inaccurate, okay, but it's a trade-off between the time and the accuracy. So you can decide what's the sample rate you want. Okay, if you think 1 million is not accurate enough, you can use 10 million or 100 million. Okay, rather than use a billion. Next is in K-means there's only I think only one parameter. The main parameters is K. What's the right number of the class K? We don't know what's the right number. You just try it start from one cluster. I said from one cluster means all the data belong to the same, and you just calculate the average of the centroids. Okay, and then you can increase 80 more clusters from 1, 2, 3, 4 until 100, 1,000, or to 1 million. Okay, so you just increase the number of clusters, and but when you increase your number of clusters, actually your loss will be decreased. Okay, so but we don't encourage you use more clusters. Yeah, if you just every data point is a cluster, you can have the smallest loss, right? Each data is just itself is a centroid of the cluster. Your loss will be zero. But it's not what we want, right? We hope you use just a few clusters, but it can generate a very good classification result. Okay, so use more clusters is not good for classification or any other application. So you should add some penalty. When you add more clusters, you should add some penalty to increase its loss. Okay, but the same problems come. So what's the penalty you should use? Okay, it's also a problem. Okay, so it's always a problem. You cannot get rid of the issue of the number of K. 好，就是你要选择到底要用多少个群，好，这永远都是个问题啊。好，就算你用了一些这种方法，然后加了一些什么旧的惩罚措施什么的，好，那都你最后还是有很多参数的去设，好，所以这个是无法逃避的。这是 K-means 最主要的，好 ，K 设的好，你那个分出来的效果就会好。好，那到底 K 要多少才会好，你就去试。好，从 从1啊、100啊、1000啊、1万啊、100万啊，你都可以试。好，像10亿笔的资料的话 ，for the data set contain 1 billion data points， so you can use 1 million clusters. It means the average every cluster contain 1,000 data points. It looks a good size of a cluster. Okay, or there's a heuristic set up by using square of your data of the number of your data points. Suppose you have 1 million, and you just take a square root of the 1 million data points, you get 1,000, right? And the 1,000, you can use 1,000. It's okay. Okay, it's a heuristic. It's a heuristic set configuration for the number of k. 就是有一个经验的法则，就是看你的资料量多少。如果说你是100万的话，你就开根号，那就是100万的开根号就是1000嘛，你就用1000个群。如果说你有10亿笔的话，它是10的9次方嘛，你就开根号就是10的4.5，大概就是2万吧，2万多个群 ，K 就设2万多这样，3万多，应该是3万多。这个就是一个经验了，但是实际上现在10亿笔资料，很多人都是用100万的群，平均每个群就1000笔资料，因为这样群的 size 不会太大，1000笔资料对于你也是那个社区是比较好的一个设定，所以看情况 ，case by case，OK， to say the case， and you should did a lot of experiment on it. Try to find the best choice of K. Okay, so is there any algorithm you can choose the number of clusters by using you don't need people to determine it. Maybe there's an algorithm can determine how many clusters. So here is the algorithm called the DB scan. It's called the full name is density-based spatial clustering of applications with noise. Okay, called the DB scan. Alright, let's try to address a problem in K-means. There are two main problems in K-means. First, K-means have to specify the number of clusters, based on the assumption that each cluster should be compact and spherical. But in DB scan, you don't need to specify the number of clusters, and you can handle various data distributions, and you can handle some like arbitrary shapes clusters. Means the data distribution can be arbitrary, and also it can handle noise and outlier. So these 2 points cannot be handled well in K-means, and you don't need to specify the number of clusters beforehand. 所以 DB scan 它不用去先给定说你要有几个群，而且它可以处理这些 outlier noise，然后可以处理任何一个形状的那种 data。Okay, so here is some example. Show you first. Okay, so in DB scan, let's suppose there are some artifacts data distribution like this. Okay, so it's like donuts, and I want to divide it into 2 clusters. In K-means, if you apply K-means with 2 clusters, it will be separated into left and right, or up or down, like this. But in DB scan, just 2 clusters, the distribution like this. So it means the K-means cannot handle such a data distribution like this. It cannot handle it very well. But DB scan can do it very well. And there's another data distribution like this. Again, DB scan do it very good. And it's for some data distribution like this. Here, K-means can do it very good like this. In DB scan, it's only generate 2 clusters, and some clusters are just surround. the blue cluster is a little bit weird. And here, you see, the DB scan can generate 3 clusters automatically. You don't need to specify how many clusters. In k-means, you have to try, and then you can find out when k is 3, you can get a very good result. But you have to try several times, set different k. And here, you can see if we set a wrong number of the clusters, suppose it's k3 here, you just separate this data point into 3 different areas. But the DB scan, it knows only one cluster. Okay, so we show some advantages. The DB scan can outperform the k-means. So how can do it? Okay, so let's okay, in DB scan there are 2 parameters. Key parameters. One is EPS, is the radius of your neighborhood around the data point. Your search inside your neighborhood, inside the radius, we consider we are neighbors. Okay, so it's called EPS. The second parameter is minimum points. This means during the radius, how many data inside my radius. Okay, so it's the minimum numbers. If you don't have the sufficient numbers of your neighbors, so you will be considered as a noisy, or you will not be a core point. Okay, so each data point, based on these 2 parameters, we can define, can be classified into the 3 different classes. First, the data point is assigned as a core point. If the data point P at least sufficient neighbors inside the radius. And the second type is a reachable point. So Q is reachable from any other core points. And Q is not to be a core point, but it's reachable. Means Q and P. P can reach Q. So it's neighbors to reach it. So it's called reachable points. And the reachable point can be core points in the issue, but it's not necessary to be a core point. And the outlier points, if there's no any point can reach it, it will be considered as an outlier. Okay. And the core point, so for each core point, they can form a cluster. They just automatically form clusters. Okay, so with all the reachable points, they form a cluster. So this is why how they generate the cluster automatically. And for the non-core points, we call it edges. And use this example is from this picture is from the Wikipedia. Okay, you can find it. And here we show, in this diagram, we show the minimum points is 4. And so you can check for the point A, we have a search radius here, and we have to check how many neighbors, how many points in the radius. So you can check including itself, 1, 2, 3, 4. There are 4 points in the radius. So all these points are the A's neighbors. And because it's satisfied our threshold, so the point A can be considered as a core point. And based on this neighbor, okay, when we identify A as a core point, okay, based on its neighbors, okay, we'll find its neighbors to check again the neighbor's radius, and this point is radius. How many data points? 1, 2, 3, 4, 5. 5. Okay, it's belong to the core points. and also its neighbors. Again, we can visit its neighbors. Okay, this point is also a co-point, but its neighbor for the point B. Point B is radius is the yellow one. You can see how many data points in the radius. 1, 2, only 2. So its points, its neighbors are insufficient. So it cannot be a co-point, and we consider it's just an edge. But A, B can be reachable from A, right? A just visit its neighbor can reach B, so we call it a reachable point. And there's also C has the same situation. Okay, so all the rate points, they are, because they have sufficient neighbors, so we call they are co-points. And the B and the C, they are reachable points. And all of them, they form a cluster. Okay? And how about point N? There's no any point can reach N, right? And in N, you can see in this radius, there's no any neighbor, no any data points. So, okay, and it cannot reachable for any A, B, C. So we consider N is an outlier. We just remove it. And only one class here. Okay, any problem? Okay. So here is the algorithm. A serial code. So you have to give the database and define your EPS and your radius, your search radius and the minima points as your neighbors, the minimum neighbors. So the C means the clusters. Okay, so for each data points in your data set D, you just visit all the data point P, and to search, you just use the region query given a point P and in a certain radius to find its neighbors. All these neighbors, you just check if it contains insufficient points in its radius, we will mark it as noise. And then the next is expand the cluster. If you just use the expanded clusters to expand from your core points and to your any reachable points in here. So if P prime can be reachable, okay, you just add P prime to the cluster C. Okay, just apply these two functions, just two main functions. You can perform the. And also in scikit-learn, I think in Python's library, they also implement this algorithm. You just code just one line, specify your database and your training data and your EPS and the minimum points. Then you can run it. Okay, so it's the result. Okay, so the pros and the cons for DB scaling. The advantage is no need to specify the number of clusters. It will generate suitable clusters for you, and you can find arbitrary shape of clusters and robust to outlier. But the disadvantage, including is not deterministic. Okay, sometimes it will generate a different result. And when you check the points with different orders, the result sometimes will be different. But the probability is very, very small. And it's difficult to tune the EPS and the minimum points. So even you don't need to determine the number of clusters. But to determine the EPS, you have two more parameters to determine, to specify. So sometimes they are very difficult to tune. Okay, especially for the high dimensional data. And if the data class data, they have a different density. Okay, so it means some Some clusters they have very dense distribution data, but some clusters they have very sparse. Okay, so it will not be very good for these points. So for example, some clusters, the distribution like this. Okay, but another data distribution like this. They have, you can see it's very different distribution, right? So in this distribution, you can use a small EPS, use small radius, but in here you have to use a higher radius. So it's difficult to think, and cannot handle such a two different distribution density. If they are different, it cannot handle such a situation. But the K-means can handle such a situation very well. And let's repeat one more. The time to run DB scale is very time consuming. You have to spend much more time than K-means. Okay, it's very time consuming. So it's depend on. So my suggestion is you just try K-means and DB scale and run on different computers and pick anyone you think can perform a good cluster for your data. Okay, both are very good, and widely used by the data scientists for you to do some data visualization, data engineering. 这都是非常好的，对资料科学家都是 DB scan 或者 K-means 都是非常好的工具。那各有各的优缺点，没有说谁一定就比较好。Okay, and also they provide the hierarchical version. For K-means, they already have a hierarchical version. DB scan also has a hierarchical version. Okay, so you can, if you are interested, you can find the information by yourself. Okay, any problems? Next, we will talk about the hierarchical clustering. Hierarchical clustering is used a tree structure to organize your data and to organize your cluster results. There are two different methods. One is bottom up. We call it the hierarchical agglomerative clustering. Bottom up, from bottom to build the cluster to up to the final cluster. And another way is the top down, from top to bottom. Okay, two different ways to build your cluster. Okay, so first is the agglomerative cluster. We call the HAC. Okay, so agglomerative means we just group the clusters if they are very similar. We just group them together, become a bigger cluster. So that's why we call it agglomerative. Okay, so in here you have to define a measure to determine the similarity between any two clusters. Okay, so first you have to define the similarity between two clusters. And then we start with each data point is a separate cluster. So each data point is a cluster itself. Then we repeat merge any two clusters to find which one has they are most similar. After they merge, then we will merge these two together into a bigger one cluster. Okay, just repeat until all the data points are merged together, and then now you have only one cluster. So it's we call it agglomerative cluster. Based on this, the final result we will build a tree hierarchy, and such a structure we call this as dendrogram. This is an example of a dendrogram. So you can see here are several different documents. Okay, each document we use just one sentence to present it. And from this, you can see. Okay, so here these two documents are merged together first because they are mostly similar. In the grammatic classroom, you have to compute any two clusters to see which similarity is the highest, then merge them together. So here is two. It means you have to combine any two documents and to calculate their similarity to find the maximum similarity, then merge together. For example, these two are most similar. Okay, we merge them first. Then the second merge is these two documents. You see, we merge them together, and also these two documents. Okay, these documents have a very similar sentence, so that's why they have a high similarity. And merge together. You can see which one merge. Okay, until the final one, all the data points are merged to one cluster. And this merge form a history, right? How they merge together. This tree, we call it a dendrogram. Okay, just show the merge history about just specify, show the relationship between these documents. And here you can see there are two vertical lines. Here you see in 0.4 there's a vertical line. This vertical line can be used. You can set up a threshold. We can say, okay, if there's similarity, if above 0.4, okay, I use this vertical line. You can divide the whole group into several clusters from their intersection. So here is the first cluster, the second cluster. Any the intersection between the vertical line form a cluster. 1, 2, 3, 4, 5, 6, 7. You can use it to generate dozens of clusters. Okay, so in algorithmic clustering, you don't need to specify the number of clusters, right? You just merge it automatically. So after all, it will be merged into only one cluster. But if you want to make it to be flat, to make a flat cluster, okay, you can determine set a threshold 0.4, suppose. Okay, and the intersection between each branch just form a cluster, and each cluster is as a flat cluster, and you can automatically generate dozens clusters with flat structure. Okay, any problems? 好，所以你在做这种阶层式的这种群聚的东西的时候，它不用给说你要分几群，不用，它就一直合并到最后只剩一群。好，可是如果说你想要用这样的结果，好，这样就是一个树状图，它就是告诉你它怎么合并的历史，它都告诉你。那如果说你想要用这个图去产生一个平坦的，不是这种树状的，然后就自动产生一些群的话，你就设一个门槛值，好，然后就是它的焦点，这就是一个 cluster， 这是第二个、第三个、第四个，每一个 intersection with the branch form a cluster， 好，就会产生大概20个左右的 cluster， 它自动产生。你只要设定不同的值，它就会产生不同数量的 cluster。好，这个 cluster 就跟 k-means 一样，就是平面的 cluster。Okay, so it's called a hierarchical agglomerative cluster. Okay, any problems? So it's an algorithm, so just give it. Okay. Okay, so the time complexity is n cubic. Okay, so compare with the k-means, which is faster, you think? According to your intuition, which one should be faster? Biological or k-means? You think k-means is faster? Raise your hand. Okay. Alright, so yeah, k-means is faster. Okay. This is very time consuming. Okay, you see the time complexity n cubic. Yeah, so it's very time consuming, especially for n is very big. Okay, because you have to take any two pairs to compute their similarity, so it's very time consuming. Okay, so I think we can start our course today here. And next time I will talk about how to define the cluster similarity. Okay, between is a main measurement to do the hierarchical clustering. Okay, so it will be our next topic.